In this video, we're going to be going over what an AVL tree is, why we need it, balance factor, the 4 rotation cases, step-by-step insertion with rotations, how to detect imbalance, time complexity, tested things, and common mistakes. So first of all, let's talk off with what is an AVL tree. It is a binary tree that automatically stays height balanced. So it's a self-balancing binary tree. It gets its name from Adelson, Velsky, and Landis. And the goal is to keep operations O of n of O of the log n. I meant to say O log n. Why do we need AVL trees? Or why? Well, that's because when you have a normal BST, if you insert 1, 2, 3, 4, 5, you're gonna get a skewed BST that looks like this. 3, 4, 5. The height is going to be 4 by counting the edges. This is the longest path that you could take and also the only path. And your search time is going to be dependent on the number of nodes. You're going to have an O of n search time. This is bad. So what AVL trees do instead is they're going to replace after, insert, and also delete. Now, let's talk about balance factor. Balance factor. So, your balance factor, BF, is going to equal to the height of your left subtree minus your height of your right subtree. So for every subtree, for every node in AVL, the balance factor must be -1, 0, or +1. Now, if it becomes +2 or -2 or something else that's greater, so like -3, -4, +3, +4, this is unbalanced. And then what you do with unbalanced things is you have to rotate them. So let's say we have 20 or 30, 20, 10. So the heights of this is going to be height of 0, height of 1, height of 2. So then we're going to calculate the balance factor here. Balance factor, we're going to look at the left height and the right height. So it's going to be 1 minus -1, which is equal to 2. So this is bad. This is unbalanced. Now let's talk about the 4 rotation cases. 4 rotation cases. So basically, you have everything split into these. So you have case 1, which is going to be left, LL. So this happens when the node becomes left heavy and a new node is inserted in the left subtree of the left child. So let's say that you are inserting increasing order. This is going to look like 30, 20, 10. Now we're going to fix it with a right rotation. So this is going to result in, we have a 20 here, 10 here, and a 30 here. Now let's talk about our case 2, where you have right, right, RR. So this is going to be a mirror of LL. So let's say we want to insert, again, 10, 20, 30, but not in decreasing order, instead in increasing order. So it's going to be a mirror, therefore it's not just a mirror, it's also a mirror, but it's also flipped vertically as well. So it's going to be 10, 20, 30. Now if this is unbalanced, so then you're going to have a left rotation. This is going to result in looking 12, 10, and 30. Now let's talk about a third case where you have left, right. In this case, LR, insert causes left heavy, but inserted in the right subtree of your left child. So let's say we want to insert 30, 10, 20. So it looks like this, 30, 10, 20. This is not LL yet. So your first step is you have to left rotate at 10, and then your second step is going to be right rotate at 30. So this is going to end up looking like this, 20, 10, 30, and it's now it's a balanced binary search tree. Now let's talk about case 4. So case 4 is your right, left, RL, and this is going to be a mirror of LR. So this is going to be when you insert 10, 30, 20. So let's say you have a tree that looks like this when you insert those 30, 20. First, you're gonna right rotate at 30. Secondly, you're gonna left rotate at 10, resulting in 20, 10, 30. All of these trees have the same result because we want it to be balanced, but we have different starting positions. Okay, now let's talk about the mechanics of the rotation. So you have a right rotation. We're going to look at the before, and you're also going to look at the after. I'm also going to look at this for multiple. So let's say before you have a Y, X, and a T1. And then after, you're going to have an X, T1, Y. Here, Y becomes right child of X. For a left rotation, you're going to have X, Y. Afterwards, you're going to have Y, X. And here, X becomes left child of Y. Now let's do a AVL insertion example. So let's say we want to insert in this order 50, 40, 30. You're gonna first have 50, and then secondly you're gonna have 50, 40. We can see that this is balanced. So now after this we're gonna have 50, 40, 30. Now the balance factor at 50 is equal to 2. So that means that you have to go through a right rotation at 50 in order to fix this, so to make this balanced again. So it's going to be 4. You're going to have 40, 40, 30, and 50. Now it's balanced again. I did not mean to put that there. Now it's balanced again. Let's talk about height in AVL trees. So height is going to be stored at each node in order to compute your balance factor fast. Usually it's structured like this. Class node, int data, node left, no left, right, int height. Then after each insertion or rotation, you're going to update the height. So you're going to have height is equal to 1 plus the max height of the right. Now let's talk about the time complexity. So for AVL trees, they keep balance, so that means that the height is approximately log n. So that means that your search, insert, and your delete are all going to be O log n. Now your worst case of your AVL tree is going to be 1.44 log 2 n. But this worst case is still much better than a normal BST. Usually what you're going to have to do is you're going to have to identify which rotation case that you have. So like here, which rotation case do we have? Like which one of these setups do we have? And which one are we going to be required to do? Are we going to have to do a right rotation? Or are we going to have to do a left rotation? You're going to have to ask if a tree is AVL valid, which means that it stays height balance automatically. Also, you have to compare your AVL versus BST time complexity. So here is your AVL time complexity. And you also have to perform that rotation manually. So when you see these rotations, you have to be able to do this when you are rotating. And you also have to compute your balance factor. Remember, your balance factor formula is going to be, where's your balance factor formula? Yeah, wait, your balance factor formula is, you have your height here. Yeah, here's your height. Your balance factor formula is going to be left and right height. Height of your right minus your height of your left. So I'll just write that here. So yeah. Now here's a trick for you. So if you have an unbalanced node with a balance factor equal to +2, that's going to be left heavy. Now, let's write all the things for left heavy. So this is left heavy. And this is if left child greater than 0, that means it's left left. If left child less than 0, it's left right. Now, let's say, when do you have right heavy? You have this when you look at the right child BF. So if right child BF is less than 0, it's right right. If right child BF greater than 0, it's right left. Now, again, let's do a comparison between AVL versus red, black. If you cover this, usually data structures, AP CSA does not cover this, but data structures likely will. So AVL, it's more strictly balanced, You have faster lookups. Red black, on the other hand, is less strictly balanced, but you have faster insertion, deletion. Now, we can also do some more practice problems with AVL. Yeah, we have the space to do that. So let's say we have a question here. Let's insert in order some examples. Let's insert 30, 20, 40, 10, 25, 22. This is going to cause an LR double rotation. Okay, so first you're going to insert 30 here. Now you're going to have to insert 20, so you have 30, 20. Now let's compute the heights. So your height is going to equal to 0, your height is equal to 1. So your BF here, balance factor here, is 0 minus -1 equal to 0. That's okay. So now this is taking up so much space, so I'm just gonna do it like this. So now thirdly, I'm gonna need a little bit more space here. You're gonna insert 40. So inserting 40, you're gonna have 30, 20, 40. We can already see that it's balanced. Now after that, we have to tackle 10. So in order to tackle 10, we're gonna have 30, 20, 40, 10. So your height is 0, your height is 1, your height is 2. Now your BF of 30, I should write BF of 30, is equal to 1 minus 0 equal to 1. That's okay still. Now if you insert 22, or 25, I mean, you have 30, 20, 40, 10, 25 fits in right there. We can see that it's still gonna be, this is gonna be balanced, so we're okay. Now 5, we gotta insert 22. So we're going to copy this over. We're going to end up inserting 22. We can see that 22 is less than 30, so you're going to go left. And we can see that it's greater than 20, so you're going to go right, and then you're going to go left. So let's update our heights. So that's unbalanced. So now we're at left heavy. Now, if you're at left heavy, let's check child 20. We're actually running out of room, so I'm going to just move this down here. So we're going to check child 20. So BF of 20 is going to be 1 minus 0. 1 minus 1 is equal to 0. So wait, so we're like, is it right heavy? But now we have to calculate the rest of them. So we see height of 10, H10 is equal to 0. We can see that H25 is equal to 1. So actually, so our BF of 20 is going to be 0 minus 1. No, yes, 0 minus 1. So that means that it's going to be left heavy with a right heavy child. And when you have that, that's going to be a left-right case. So now you had to do the left-right rotation. So first what you're going to do is you're going to left rotate at 20. So we're going to call this step 6. And then for 7, we're going to have a right rotation at 30. So we're going to take our tree at 20. We're going to have 25. 22. And after this, we're going to rotate it at 30. So where's 30? So I'll just highlight these. So 20. Yeah. And then here, we're going to do it at 30. So 25. And then your final result is the correct BST, so that's how you know you did everything right. Now it's balanced. Now let's do our